Okay, cool. So we're going to use a limit definition. We're going to do a lot of limit definition today. So we're going to do the limit as h goes to 0 of f of x plus h minus f of x all over h. And then we're going to simplify. Well, I guess we're first going to plug in the function. So the function here, f of x is x cubed. F of x plus h is just x plus h quantity cubed. I want to make sure everyone's aware. X plus h quantity cubed is not x cubed plus h cubed. It's x cubed plus 3x squared h plus 3x squared plus 1h cubed. There's kind of a pattern. In fact, it's worth mentioning right now. So yeah, we'll go to the other side here. We'll come back to this side. So there's this thing called Pascal's triangle. And it kind of corresponds to the coefficients of x plus h to higher and higher powers. For example, if I write x plus h to the 0th power, well, we know that anything to the 0th power is 1. It's not very exciting, I know. I guess I'm pounding my finger first. And then x plus h to the 1st is just x plus h. I'm going to write it in a very kind of specific way. I'm going to write it as 1x plus 1h. And hopefully we know that x plus h squared is x squared plus 2xh plus h squared. Which I'm going to write as 1x squared plus 2xh plus 1h squared. And what I want to point out is there's actually a pattern here that exactly syncs up with the first 3 rows of Pascal's triangle. So Pascal's triangle is a triangle. You start with 1s on the outsides. And then to get the middle numbers, you add the 2 kind of numbers above. So I have a 1 on the outside, 1 plus 1 is 2, and then a 1 on the outside. And then for the next row, I have a 1, and then 1 plus 2 is 3, and then 2 plus 1 is 3, and then a 1. And then for the next row, I'd have a 1, and then a 4, and then a 6, and then a 4, and then a 1. And so on and so on and so on. It goes on forever. And there's lots of really, really interesting patterns in Pascal's triangle. The one we care about today is the fact that each row of Pascal's triangle gives the coefficients of this thing which is called the binomial expansion. So when you take x plus h to the 0th, you get 1. When you take x plus h to the 1st, you get 1x plus 1h. When you get x plus h squared, you get 1x squared plus 2xh plus 1h squared. And the pattern here is that you start with x to whatever your highest power is, like x squared, and then you just you decrease the power of x by 1 each term, and you increase the power of h by 1 each term. So we can say that x plus h cubed is going to be, well, I know the coefficients are 1, 3, 3, 1. So it's going to be 1x cubed plus, then I'm going to decrease the power of x by 1 and increase the power of h by 1. So I'm going to get a 3x squared h to the 1st, and then a 3x to the 1st h squared, and then a 1 h cubed. And we can do the same thing for x plus h to the 4th. X plus h to the 4th would be 1x cubed, 1x to the 4th, or just x to the 4th, plus 4x to the 3rd, h to the 1st, plus 6 x to the 2nd, h to the 2nd, plus 4 x to the 1st, h cubed, plus 1 h to the 4th. And this will work for x plus h to any nice positive integer power that you like. So if you have to do something like x plus h to the 4th or x plus h to the 5th and you don't remember it, instead of trying to like multiply it out, write down Pascal's triangle until you get to the row where the second number in is the power you're looking for. Right? So I think of like, oh, if I'm doing x plus h to the 3rd, I'm looking for this row with the 3 in it in the second spot. I'm doing x plus h to the 4th, I'm looking for this row where the 4 is the second term in the spot. Okay, so back to what we're doing. That means that f of x plus h equal to x plus h cubed. Well, so we're going to write this as the limit as h goes to 0 of x plus h cubed minus x cubed all over h. And then we're going to expand out x plus h cubed like we just did on the other side of the board. We're going to write this as the limit as h goes to 0 of x cubed plus 3x squared plus 3xh squared plus h cubed. That's all of x plus h cubed minus x cubed. And I don't really need those parentheses there. I just want to write them to really emphasize that, oh yeah, x plus h cubed is all of this. It's x cubed plus h cubed, and then there's some middle terms as well. Can't memorize those parentheses, so I don't really need them. And then the thing that's going to happen, like every time, is going to happen. And by the thing that's going to happen every time, I mean, we're going to cancel out all the things, or we're going to hope that all the things on top that don't have an h cancel out. X cubed doesn't have an h. It cancels with negative x cubed. Awesome. Nothing else cancels, but everything else has an h, so that's okay. Sometimes some of the h things also cancel, but for sure, all of the not h terms should cancel out eventually. And then the rest of the things have an h in it. So we factor the h out. So we get the limit. This h goes to 0. Let's see. I'm going to factor out an h. Oh, sorry. So there should be an h here. I didn't write it, right? There's definitely, right? It's x cubed plus 3x squared h. I forgot to write it down there. So that should be a 3x squared h plus 3xh squared plus h cubed. And then I'm going to factor or divide out an h from each term. So I'm left with a 3x squared there. I'm left with a 3xh to the first. And I'm left with an h squared. All over h. This h cancels with that h. And that's what our ultimate goal is to cancel out that beginning h in the denominator, right? We are really trying hard to cancel out this h. And oh, we just did it. Great. After you cancel out that h, then you can actually evaluate the limit. So you can say, oh, now I'm taking the limit as h goes to 0 of 3x squared plus 3xh plus h squared. And now that I'm not going to worry about dividing by 0 when I plug in 0 for h, I'm just going to get 3x squared plus 3 times x times 0 plus 0 squared, which is just 3x squared. So this is the derivative of x cubed. If f of x is equal to x cubed, f prime of x is equal to 3x squared. Great. Let's do another one. So we're gonna do x plus h. We're gonna do x to the fourth. So I'm gonna erase this. Well, maybe I'll leave it up for a second so that we can refer to it before I erase it. For those of you that might have joined this a minute or two late here, I was talking about how Pascal's triangle, which is that triangle there, where the numbers in the middle you get by adding these things together. So like 1 plus 1 is 2, and then 1, 2, 1, you get 1, and then 1 plus 2 is 3, and 2 plus 1 is 3. Here, 1 plus 3 is 4, 3 plus 3 is 6, and so on and so on. Those numbers in Pascal's triangle give you the coefficients when you multiply out x plus h to higher and higher integer powers. So if I want to find the derivative of f of x equal to x to the fourth, again, using the limit definition of derivative, because even if you have already learned the rules of taking this derivative, we're still talking about that. So it's going to be the limit as h goes to 0 of, again, f of x plus h minus f of x all over h. If you're ever asked to find the derivative using the limit definition, I highly recommend writing it out this way first, even though you're going to go straight to plugging in whatever the function is. It's still nice to write this out. It's also nice to let the person grading your work know that you know what the limit definition is. Okay, so let's erase this. So I'll leave this up for a second. So that's going to be the limit as h goes to 0 of f of x plus h. That's going to be x plus h to the fourth minus x to the fourth all over h. And just like last time, we expect the not x things to end up canceling out on top, then being able to factor out an h from all the things left that have an h in them, and then canceling the factor out h with the h in the bottom. And that's what's going to happen. Meaning the limit as h goes to 0. Let's see. So this multiplies out as all this. So it's x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus 6, sorry, not 6, plus h to the 4th minus x to the 4th all over h. I'm going to be a little bit less step intensive here. I'm going to cancel the x to the 4th, and maybe it will be. And then I'm going to factor out h from the top. So factoring on the h, I get a 4x cubed. I get a 6x squared h. And here's what's going to happen every single time. The first term that's left, the one that's x to a power and h to the 1st power, when you factor out an h from there, you're not going to be left with any h's left. But everything after that has a power of h that's more than 1. And so even when you factor out 1h, you're still left with h's in all the remaining terms. And so once you eventually take the limit as h goes to 0, well, these cancel. And then all the remaining terms that have h's, those go to 0. So the only one that really matters is this one right here. So this ends up being 4x cubed plus 0 plus 0 plus 0, which is 4x cubed. So the derivative of x to the 4th is 4x cubed. Let me show you one more example, and then we'll talk about kind of what the formula is. And I'm imagining many of you already know what it is. It's fine. Let me admit the person who just came in here. Sorry, 1 second. Not drop the pen on the floor. Okay. So let's say I want to take the derivative of, using the limit definition. Let's say I want to take the derivative of x to the 7th, which I know is the limit as h goes to 0 of f of x plus h minus f of x all over h, which in this case is going to be the limit as h goes to 0 of x plus h to the 7th minus x to the 7th all over h. And here's the thing. I really don't want to actually write out x plus h to the 7th. I could. We could do it. But I don't really need to. Here's all I need. Let's go to the other side for 1 second. Yeah. So here's the work we just did. I'm going to erase it. I know. It's terrible. I'm going to write down kind of Pascal's triangle. At least to the part that I need. So we had what we had. So I shouldn't have erased what we had first. We had 1, 1, 1, 1, 2, 1, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, whatever, 1, 6, 15, whatever. Sorry, my 6 is a little scrunched in there. And then 1, 7, 21, etc. So here's what I know. I know that x plus h to the 7th is equal to x to the 7th plus 7x to the 6th, h to the 1st, plus 21x to the 5th, h squared, plus lots of other things that have higher and higher powers of h, right? There's something, I'm going to write c for a constant. There's some constant times x to the 4th, h cubed, plus some other constant, x to the 3rd times h to the 4th, all the way to h to the 7th. It's not that we couldn't find those things, we just don't really need to. So here's what happens. So I'm going to use this in the place of x plus h to the 7th. So here's what I'm going to get. I'm going to get the limit as h goes to 0 of x to the 7th plus 7x to the 6th, h to the 1st, plus 21x to the 5th, h squared, plus lots of other things that have higher powers of h's. Last one of those is h to the 7th. And then finally, minus x to the 7th. And just like in the previous two examples, the not h things cancel. The x to the 7th cancel. And so then I'm going to factor out an h or anything else. And we know that everything else has an h. Here's an h to the 1st. There's an h squared. The next term, if I wrote it, would have an h cubed. The terms after that, h to the 4th, all the way to h to the 7th. So here's what I'm going to get when I factor out an h. I'm going you get h times 7x to the 6th plus 21x to the 5th times h plus something times x to the 4th times h squared plus something times x to the 3rd times h cubed plus all the terms that have lower powers of x and higher powers of h plus all the way to the very last thing when I factor in h will be h to the 6th. And here's what I really, really need to strongly emphasize here. Each of these terms, right? This term and all the middle terms I didn't write, all of those have an h for sure. So then when I cancel this h here, if I take the limit as h goes to 0 of 7x to the 6th plus a bunch of things that all have an h in them, all these things have an h. So the limit as h goes to 0 of something times h plus something times h squared plus something times h cubed plus all these things that have times an h in them, all those are going to go to 0. So you're just going to get 7x to the 6th plus a bunch of zeros, which is going to be 7x to the 6th. And so this leads us to thinking about, well, it looks like we've got kind of a pretty strong pattern here. We found that we probably know some other ones too, but we definitely found that, right, if f of x equals x cubed, the derivative was 3x squared. And if f of x was x to the 4th, the derivative was 4x cubed. And we skipped x to the 5th and x to the 6th, but maybe we'll fill them in. Oops, if x is equal to 5, if it equals x to the 5th. But we definitely did f of x equal to x to the 7th, and we got that the derivative was 7x to the 6th. Okay, so let me ask you guys for your guesses. If you had to guess, or maybe you know, it looks like each time we take the derivative, we get a coefficient, right? If I take the derivative x to the 3rd, I got 3x squared. X to the 4th, I got 4x cubed. X to the 7th, I got 7x to the 6th. So if I was going to take the derivative of x to the 5th, it would be a pretty good guess that the coefficient out here would be what? People writing things already. Definitely. We're definitely going to get a 5. Ooh, sure. And then the power seems to be 1 lower. And in fact, that is what's happening here. The derivative here of x to the 6th would indeed be 6x to the 5th. And so what we see is what we have is the idea of the power rule. The power rule says if f of x is equal to x to any power, doesn't have to be an integer, it can be any fractional, irrational, positive, or negative number, then the derivative f prime of x is equal to that power times x to the 1 less power. So the derivative of x to the p is p times x to the p minus 1. And it works for any power. And the idea behind it is essentially the same as what we did over here, right? So you can't show this for any power. You can show it for any positive integer power, that you can always kind of write x plus h to some power, that's a positive integer, expands out this way, and you always get this thing where the first thing, x to the whatever, cancels with x to the whatever there, and then the second thing, you factor out an h, and you're left behind with just the thing that's going to be your derivative. And all the other things have too many h's and they go to 0. So are there any questions about this power rule?
Since you said it only goes for positive, what do you do if it's like a negative?
So here's what I'm saying. I'm not saying it's only true for positive integers. I'm saying we can only prove it this way for positive integers. So no one's going to ask you to prove the power rule, but I'm just saying it is true for any number. In fact, let me show you some examples. So yes, the power rule works for any number. And so it is for any power, I should say. So it is definitely true that, and sorry, I should talk about some notation here for just 1 second. So sometimes people are going to write something like this and say, okay, f of x equals x to the negative 6, and we're going to write the derivative as f prime of x equals negative 6 x to the, what should my new power be?
5.
Well, so it's not positive 5.
Oh, it's -1, right? So -7.
Right, exactly. Sometimes people make the accidental mistake of saying it's -5 because they're like, oh, it's 1 less, but 1 less than -6 is -7. But sometimes people will prefer a different notation. Like they might write that the derivative of, so d dx is the symbol for take the derivative of whatever comes after it with respect to the variable x. The derivative of, I'm going to take a different thing. Let's say, x to the 19th power is going to be 19x to the 18th. This is the notation I probably prefer to use because it's more compact. It's less writing. I don't have to write out f of x equals this, f prime of x equals that. I just can say, oh, the derivative of f of x equals f prime of x. It kind of gives you more information in one shot. But I'll probably use all sorts of notations. So I just want to make sure everyone's comfortable with this. That when I say d dx, or I could say, d dt of t to the 7/3, I'm just saying take the derivative of t to the 7/3 for the variable t, or with respect to the variable t. And so we're just going to still use the power rule. So the power rule, even though we can't prove it using the method we use for the other thing, for any other powers that aren't positive integers, it still works for any power, whether it's positive, whether it's negative, whether it's a fraction, whether it's an integer, whether it's some weird irrational number. So this would be 7/3 times t to the 7/3 minus 1 is 7/3 minus 3/3, which is 4/3. Or I could say the derivative with respect to y of y to the pi, it's still a power rule, right? You still got a variable to a constant power, right? Pi is a constant number. And so the derivative is, well, just like here, where you multiply by the power and subtract them for the power, we're going to do the same thing. We're going to multiply by the power, so pi times y to the, what's my new power going to be? Yeah, exactly. Pi minus 1. And there's no other way to write it. We don't want a decimal part, right? You definitely should not write this as 3.14 times y to the 2.14, right? That would be close, but not exactly the same. And we want an exact answer. That's the answer we're going for. But let's see here. Yeah, no, okay. You might not be super convinced about this. So let's look at just a couple examples to see things that we know should be true, but we want to make sure they're true. So I'm going to show you 2 examples to kind of convince you that, oh yeah, the power rule really does work even if you can't just write it out. For example, I want to take the derivative of the square root of x, which I am going to use the power rule for first, but then I'm going to show you it's true using the limit definition of the derivative. So that's equal to the derivative of x to the 1/2, which is equal to 1/2 x to the minus 1/2. Right? I brought the power. We usually say we bring the power down and multiply by it. So I multiply by 1/2, and then my new power is 1 less than 1/2, and 1/2 minus 1 is negative 1/2. Okay, but now we're going to do it using the limit definition. And here you'll see what I mean by we can't do it the way we were doing it before. So I'm going to do the derivative of the square root of x is equal to the limit as h goes to 0 of f of x plus h. So that's the square root of x plus h minus the square root of x all over h. And here's the thing. Before, when it was like x plus h cubed, you could just multiply it out. Or when it was x plus h to the fourth, you could just multiply it out. But when the square root of x plus h, or x plus h to the, right, you could also write this as x plus h to the 1/2 power. You can't expand that out. You're kind of just stuck. You're stuck using other algebraic methods. So that's the thing. For other powers that aren't positive integers, you have to kind of do something else than just multiply it out. It still ends up getting you the same power rule result, but the path to get there is slightly different. In this case, the path to get there is multiplying by the conjugate. We've probably even done this one before. I've at least for sure done it in one of the classes I'm teaching this quarter. And so then when I multiply that out, I end up with a limit as h goes to 0. The denominator is just h times that stuff, square root of x plus h, plus the square root of x. The numerator, well, there's a reason we multiply by the conjugate, because you get the first thing squared. So the square root of x plus h squared is just x plus h. Minus, well, the middle terms cancel. Right? This times this and this times this are opposites of each other, so they cancel out when you add them together. And then finally, you get the last terms multiplied together, but you get the last term, so you get minus the last term squared. So minus the square root of x squared is just x. And then limit as h goes to 0, x minus x cancels. You get h over h. The h's are going to cancel. Square root of x plus h plus the square root of x. Those h's cancel. So now you've got the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. And now, since we canceled the h in the denominator that we wanted to cancel, the rest of the h's just get to go to 0. And when they go to 0, you get 1 over the square root of x plus the square root of x. And what's the square root of x plus the square root of x? It's not x. What do you get when you add something to itself? Like, what's 5 plus 5? I know it's a dumb question. What's 5 plus 5?
10.
Right. Because when you add something to itself, you get twice itself. 5 plus 5 is 10, but 10 is just 2 times 5. Square root of x plus the square root of x is 2 times the square root of x, or 2 times x to the 1/2. Yeah. So I get 2 square roots of x, but I am going to actually take Karen's suggestion there and write that as 1 over 2 x to the 1/2, and then rewrite that as 1 over 2 times x to the negative 1/2. And hey, look, that's exactly what we would have gotten if we had just used the power rule. So the power rule does work even if your power isn't a nice positive integer. It works for any power. Yeah, let's do one more. Let's see, I feel like there was some, let me check out one thing real quick here. Sorry, someone had asked for a thing.
Okay.
Yeah, go ahead.
So on an exam, can we just do the power rule instead of like all that?
Yes, but you might have to do that if the question specifically says use the limit definition of the derivative to find the derivative of blank.
Oh, okay.
Right. So normally, yes, if they say just, if someone says find the derivative and they don't give any other direction, it's implied that you can use whatever rules you have learned. If someone says use the derivative using the limit definition, which they will spell out if they want you to do it that way, then you are supposed to do it that way. And typically in a Calc 1 quarter, usually on your first or second exam, they will ask you to find at least one derivative using the limit definition. That's not a guarantee, but it would be a guarantee if I was teaching the class. So just be aware. You can ask your teacher, right? You can ask them, will we have to do that on the test? That's a perfectly fair thing, I think, to ask your teacher. I'm just trying to find one thing here. Let's see, where'd that go? things are not appearing for me here. Well, I don't know what your problem is here. Sorry, I'm not talking to you guys, I'm talking to myself. Oh, there we go. Okay, we'll get to that. Yeah, okay, cool. So, so I want to do one more. So let's say I want to find the derivative. So let's say f of x is 1 over x squared. And I want to find the derivative using the limit definition. Now, first, before I find the derivative using the limit definition, let's find the derivative using the power rule. And here's what I want to make sure is really super clear to everybody. The derivative is not equal to 1 over 2x. I know the derivative of x squared is 2x, but the derivative of 1 over x squared, if you want to do it like that, you have to use the quotient rule. Or you can make your life easier and simplify it. We can rewrite this as f of x equal to x to the negative second power. And then we can take the derivative by using the power rule. So to use the power rule, you really just have to have x to a power. It can't be like 1 over x to a power or the square root of x to a power. It can only be x to a power and nothing else kind of going on around it. So the derivative of x to the negative second should be negative 2 times x to the negative 2 minus 1, which is negative 3. Great. So then let's do it using the limit definition and see if they're the same. So the derivative using the limit definition is going to be the limit as h goes to 0 of f of x plus h minus f of x over h. Things are going to be a little less nice here. F of x plus h is 1 over x plus h squared. This limit as h goes to 0 of 1 over x plus h squared minus f of x, which is 1 over x squared, all over h. And what we're going to do here that we usually do when we're subtracting fractions, we're going to multiply by common denominators. So I'm going to multiply this by x plus h squared over x plus h squared. And multiply this by x squared over x squared. So then, in the next step, I'm going to get the limit as h goes to 0. So this fraction is going to be x squared over x squared times x plus h squared minus this fraction. The denominator is also going to be x squared times x plus h squared. And I do want to multiply out the numerator because I know I'm going to need to. So this numerator, which is x plus h squared, that multiplies out as x squared plus 2xh plus h squared. And instead of dividing by h, which is like dividing by h over 1, instead of dividing by h over 1, what are we going to multiply by? Well, if you divide by a fraction, you multiply by its
reciprocal.
Exactly. So we're going to multiply by 1 over h. That's going to make things nicer. All right, so now we're going to subtract these fractions. Do the limit as h goes to 0 of, so when you subtract fractions, the denominator stays the same, right? That's why you got a common denominator, so you could add or subtract the fractions. So I'm going to have x squared times x plus h squared. And the numerator is going to be x squared, and this minus sign has to distribute. So it's minus x squared minus 2xh minus h squared, all times 1 over h. If you wanted to, you could put this right. When you multiply fractions, you just multiply top times top, bottom times bottom. So you can totally just say that h is really in the denominator here. That would also be fine. Let's simplify. The x squared minus x squared cancels. The rest of the terms on top have an h. So I can factor out that h and get the limit as h goes to 0 of, so on top I'm going to factor out an h, and we're left with a minus 2x minus h. On the bottom, I'm going to multiply this times this times this just as one thing. So it's x squared times x plus h squared times h. And then this h I factored out, And this original h that was on the bottom, right? That is my original bottom h there. Those cancel out. And after you cancel out the original bottom h, we know that we're going to try and take the limit. We're actually going to plug in, right, h going to 0. So I'm going to get negative 2x minus 0 on top over x squared times x plus 0, which is x squared. Which ends up being, if I cancel one of the x's, negative 2 over x cubed. Or if you prefer, negative 2x to the negative third. Which is exactly what we got using the power rule. So I really want to make it absolutely 100% clear that the power rule works. And it doesn't matter what the power is. Positive, negative, rational, integer, irrational, other weird thing. I also want to make it clear in two special cases that aren't that special, but they are. Well, in fact, actually, let me do a different example before I get there. So what's the derivative of 5x to the 7th? We're going to get 35x to the 6th. Now, I'm using a rule that we haven't even talked about, which is that when you have a constant multiple of a function and you take the derivative of that, you get the constant multiple times the derivative. Because what we really did here was we said, oh, that's 5 times the derivative of x to the 7th, which is 7x to the 6th. And then we multiplied the 5 by the 7 and got 35x to the 6th. And we do that all the time, right? People could ask, hey, what's the derivative of, I don't know, 9x to the 4th minus 7x cubed plus 2 square roots of x plus 1 over 4 over x to the 8th. And before taking the derivative, I would do something. I would rewrite this just a little bit, just to make sure that everything was like x to a power instead of a root of x or dividing by x to a power. So I'm going to write this as 9x to the 4th minus 7x cubed plus 2 times x to the 1/2 power plus 4 times x to the negative 8th power. Because now they're all written as some constant times x to a power. And so the derivative of 9x to the 4th is going to be, well, the 4 comes down, multiplies the 9, and we get 36x to the 1 less power, which is 3. And we just continue doing the same thing for each piece. Here we're going to get minus 21x squared. Here we're going to get, so 2 times the 1/2 comes down, you get 1, which you don't really need to write, but it's still 1, write it, times x to the 1 less power, 1/2 minus 1 is negative 1/2. And finally here, the negative 8 multiplies the 4, you get minus 32. X to the negative 8 minus 1 is negative 9. And that would be my derivative here. The two things I want to talk about that aren't that hard, but are kind of important to remember are maybe 3 things actually. What's the derivative of x? Right, it's 1. And you can either think of it, and I recommend thinking of it as, well, the line y equals x is a straight line, and its slope is always 1. And slope and derivative are kind of the same thing. So we talk about the slope of a line. Usually we talk about the derivative of a function as the slope of the tangent line. But for a straight line like y equals x, any tangent line you draw is actually the line. Right? If I take a point here and say, what's the tangent line? There it is. It's right there. It's the same. So the thing is, for a straight line, the slope of the tangent line is just the slope of the line. So for a straight line, the derivative is just the slope of the line. And so the derivative of x is just 1 because the slope of that line is just 1. But I will also mention, you could, if you really wanted to make your life more complicated, use the power rule. You could say, oh, I'm going to write it down here because I don't really want to write it in my special box. The derivative of x to the 1st is 1 times x to the 1 less power, which is x to the 0th. And 1 times x to the 0th, well, x to the 0th is 1, and 1 times 1 is 1. So you could really go the long way there and say, oh yeah, the derivative of x is just 1 by using the power rule. You shouldn't use the power rule. You should just say, oh yeah, I know it's 1 because I know it's 1 because it's got a slope of 1. In a similar way, the derivative of any constant, like 6, is equal to 0. Because the line y equals 6 is a horizontal line. Right? I'm going to draw it. I guess I can draw it here. There's y equals 6. What's the slope of y equals 6? I already said it. It's 0, right? The slope is 0, which means the derivative is 0. And it's 0 everywhere. You can also do this kind of the not so smart long way. Say, oh yeah, the derivative of 6. Well, the derivative of 6 is really the same as the derivative of 6 times x to the 0. And then you could use the power rule and be like, okay, well, that's going to be 6 times 0, x to the negative first. But anything times 0 is just 0, so you get 0. These are not the ways you should do these derivatives, but I do want to point out that the power rule always does work for x to a power. And then I should also lastly point out that if you take the derivative of some constant times x, like 5x, you're just going to get 5. And again, you can either do it because it's 5 times the derivative of x, which is just 1, or you know that 5x is a straight line and the slope is 5, so the derivative is 5. So yeah, we start doing derivatives so much that we kind of sometimes tend to kind of lose the connection to what they mean. But I really want you to remember that, oh, if you're taking the derivative of something like 3x, it's just 3 because the slope of the line y equals 3x is just 3 everywhere. Okay. Let me take a look at something here. Sorry. Not what I wanted. Sorry, let me look back in the chat real quick. Someone asked about question 3 from worksheet 4, which I'm happy to look at. I want to make sure that's what they really want because it was due already a couple days ago, which is fine. So let's take a, this is a good kind of, this is a good interlude. If I'm doing the wrong problem or addressing the wrong problem, please let me know and I will see what's right. But this is, so I'm looking at, this is, I think it's group homework 4 from Guy's class, I guess, about problem 42 in section 3.1. The graph, see the book, shows the influence of temperature on a maximum sustainable swimming speed S of coho salmon. Oh, from Lewis. I don't have access to Lewis's stuff, unfortunately. He has never added me. He's the only one who has not added me to his Canvas. So if you have the problem and you want to either send it to me in an email or text it or write it in the chat to me, that'd be great. But otherwise, I don't know what the problem is, unfortunately. Okay, great. I'll look for the email. Until then, I will do more stuff. So let me get back to my other thing I was looking at. So the thing about the power rule is it works, right? So for example, so normally, regular times, I'd be like, here's a problem, work on it. It just feels awkward to do. Like, I'd be like, work on a problem. I'd be like, okay, so I'm going to show you how some problems work. So let's look at something like this. F of x equal to x to the 10th plus the cube root of x squared plus 1 over x to the 5th minus 6. And I'm taking the derivative. And before I take the derivative, so here's the thing. If I'm going to simplify first, which I should, I don't want to write this. I don't want to write f prime of x equals x to the 10th plus x to the 2/3 plus x to the negative 5th minus 6. I know I'm eventually going to find the derivative, but I haven't found the derivative yet. I've just rewritten the function. So I shouldn't write the derivative until I'm actually finding the derivative. So she says f of x, and now I'm going to find f prime of x. It's going to be 10x to the 9th plus 2/3 x to the -1/3 plus -5 times x to the -6. So you could write plus -5x to the -6. It seems silly to write that when you could just write -5x to the -6. So that's what I would probably prefer to write. It's just -5x to the -6 minus 0, which I wouldn't really write, but I do want to point out that, oh yeah, the derivative of that is 0. Let's do another one. Let's do something like, sure, we'll do 2 more. G of x equal to, what have I got here? 4x to the -7 plus 6 over the square root of x plus 5x minus pi to the 3rd power. And once again, before we start differentiating, we should really rewrite some stuff. The other thing we actually really have to rewrite is this second term here. So instead of writing 6 over the square root of x, I'm going to erase it and write it as 6 times x to the -1/2. So now we're going to use our power rule. We're going to get, so right, the power comes out to 4 times -7, which is -28. X to the -7 minus 1 is -8. And then same deal here. The power comes down and multiplies the coefficient. 6 times -1/2 is -3. So -3x to the -1/2 minus 1 is -1/2 minus 2/2, which is -3/2. Just a reminder, when you take these derivatives, if your powers are positive, they should get smaller. If your powers are negative, they should get more negative, which is still smaller, but it's more minus. That's the right way to say that. It's more negative. The derivative of 5x is 5. And what's the derivative of pi cubed?
3 pi squared.
That is the wrong answer I was hoping for. Thank you for being so brave and saying. So this is the answer I was looking for, but it's not right.
0.
It is definitely 0. So, but people will write this to try and trick you. Because they'll be like, oh yeah, it kind of looks like x cubed. The derivative of x cubed is 3x squared. But pi cubed is just a number. It's like 25. It never changes. And things that never change are constant. And constants have a derivative that is 0. So do be careful.
So pi to any power is just a constant, so 0.
Yes, exactly. And I would encourage you, if you have a moment, graph it on Desmos. Like go graph y equals pi squared. Or pi, if you do pi cubed, you'll have to zoom out a bit because it's like 25. But you'll just get a horizontal line for anything that, so if you graph y equals something that doesn't have a variable in it, and pi is not a variable, it is definitely a constant, you're going to get a horizontal line. And a horizontal line always has a slope, aka a derivative that is 0. It's also true if you have like e, right? If you say like if y equals e to the 4th, the derivative of that is also 0 because e is just a number. It's about 2.7, and 2.7 to the 4th is just a constant. So yeah, the thing you should always be thinking of when you're differentiating is there a variable in there? Is there an x? No, then its derivative is 0 because that's a constant. Now let's see. Take a look at this thing real quick here. I don't know about that. Let's see. Yeah, I'm not sure about the problem I was just sent. It looks, I mean, not that it's nothing that isn't doable, but I have to think about it for a second. So let's continue on. So I guess I should ask, actually, let me do one more problem before I ask. So sometimes we have things that look kind of messy, like the following. For example, you might be trying to take the derivative of something like, what have I got here? X cubed plus 3x times x to the fourth plus 2. And while we will learn the product rule pretty soon, we haven't, at least I haven't talked about it. Maybe you guys have talked about it in class. I don't know if you've talked about the product rule, maybe write in the chat, yes, we've talked about the product rule. But the way I would do this without the product rule is by using my algebra skills. I'm just going to multiply it out. This is the derivative of x cubed times x to the fourth, which is x to the seventh, plus 2x cubed, plus 3x to the fifth, plus 6x. And then I'm just going to use my power rules. So I'm going to get the derivative of x to the seventh, which is 7x to the sixth. I would probably change the order of these just because they're out of order, right? At least from the usual way of writing powers from highest to lowest. So I'd probably do the derivative of this next, which is 15x to the fourth. And then the derivative of this, which is going to be 6x squared. And then finally the derivative of that, which is going to be just 6. So a lot of the time, it makes a lot of sense to first simplify an expression before trying to differentiate it. We certainly could use the product rule here if we knew it, but it's not really worth it, right? Here, it's really probably easier just to multiply the thing out than to use the product rule. And the same kind of comment goes for the next question, which is, I want to find the derivative of, say, f of x equal to x to the 9th plus x to the 3rd over x to the 4th. Now let's make this more fun. X to the 9th plus x to the 3rd minus 2x over x to the 4th. You could, once we have learned it, totally use the quotient rule here. But even if you could, I don't think you should. Because while you can use the quotient rule here for this, it's much easier to just simplify when you have an expression where the denominator is just one term x. So I can divide each of those things by x to the 4th. I can rewrite this expression as x to the 9th over x to the 4th plus x cubed over x to the 4th minus 2x over x to the 4th. And then I can rewrite each of those as x to the 9th over x to the 4th is x to the 5th. X cubed over x to the 4th is x to the negative first. Or 1 over x, but again, I want to write them as x to a power, not 1 over x to a power. And then this is going to be minus 2 over, or sorry, it would be minus 2 over x cubed, but I should write it as minus 2 times x to the negative 3rd. And now after all that simplifying, I'm finally ready to take the derivative. The derivative here is going to be 5x to the 4th plus negative 1 times x to the negative 2, so minus x to the negative 2. And then negative 3 times negative 2 is plus 6 times x to the negative 3 minus 1 is negative 4. So a lot of times it pays to simplify an expression before we start differentiating it. And then we can use this to start finding equations of tangent lines. So for example, we could say, all right, I want to find the equation of the line tangent to, what do I got here? F of x equal to the square root of x times x plus 6 at x equal to 4. And of course, to find the equation of any line, oh yes, yeah, when we totally could have used the quotient rule for this previous one, but I personally, I think for this one, everyone should simplify. I think this one is easier to do if you just simplify it. Also, the answer looks nice, right? If you can use the quotient rule here, but if you use the quotient rule, the answer is going to be kind of gross looking, which is fine, but it's much nicer if we simplify first. So I think, especially when you have a bunch of stuff divided by just one thing, it's really usually worth your while to simplify it like this and then differentiate it. But yes, you could have used a quotient. So for this one, I want to find the equation of the tangent line. I can, well, let's see, what am I trying to say here? To find the equation of the tangent line, you need two things. You need a point, you need a slope. To find the slope, we're going to use the derivative. To take the derivative, I'm still operating in the pretense that not everybody knows the product rule. So I'm going to multiply it out. So I'm going to rewrite this as f of x equal to x to the 1/2 times x plus 6. So f of x equals x to the 1/2 times x to the 1 is x to the 3/2. And x to the 1/2 times 6 is 6x to the 1/2. And then I can take the derivative and get 3/2 x to the 1/2 plus 6 times 1/2 is 3 times x to the -1/2. So that's my derivative everywhere. I want to find the slope of the tangent line at the point x equal to 4, or when x is equal to 4. So I need to actually plug in 4. So my slope, m, is going to be f prime of 4, which is 3/2 times 4 to the 1/2 power, which is the square root of 4, which is 2, plus 3 times 4 to the -1/2 power. Okay, so 4 to the 1/2 is the square root of 4, which is 2. So this is 3/2 times 2, which is 3, plus 3 times 4 to the -1/2 is 1 over 4 to the 1/2, which is 1 over the square root of 4, which is 1 over 2. So I get 3 plus 3/2, which is 6/2 plus 3/2, which is 9/2. So that's the slope of the tangent line here. We have a slope. We have half a point. To have a whole point, we need the y coordinate as well. So if x is 4, y is f of 4, which is the square root of 4 times 4 plus 6, which is going to be 2 times 10, which is 20. So now we have a point. X is 4, y is 20. And we have a slope, 9/2. And then we have to throw everything into the slope intercept, or the slope, the point slope form, or the slope intercept form, whichever one you like. I prefer the point slope. So I write my equation as y minus the y coordinate equal to my slope times x minus the x coordinate. And then I would probably leave it like this if I was allowed to, but if I wasn't, I would solve for y. So you can see y equals 9/2 x. 9/2 times -4 is -18, plus 20 is +2. Okay. So I get the impression that some of you have talked about the product rule and gross rule, but I'm guessing some of you haven't. Yeah, it's always the challenge with so many different places the classes can be. Sorry, I'm just trying to think about what we're looking at here. Okay, so someone had asked about this question from their worksheet, which does seem worthwhile, but we're probably not going to work the whole way through. So let me talk about this question, and then we'll just because why not? And then I guess we should probably start moving towards talking about the product rule. Although we kind of need two other derivatives for that, so maybe we'll do that first. Oh, yeah. So here's the problem. It's from Lewis's class. I guess I can show it to you guys for a second. Sure, I can share my screen. So here's the problem. I believe it's problem 3 that we are looking at. Researchers measured the blood alcohol concentration of 8 adult subjects of rapid consumption of 30 milliliters of ethanol, corresponding to 2 standard alcoholic drinks. The table, what's that?
I don't think we can see it.
Oh, you can't?
No, we see your messages and
That is weird. Let me stop sharing. Oh, I think I know what I did. Let me try again. Sorry about that. Yeah, I see what I did. I clicked on the wrong thing. Okay, how about now?
yeah.
Great. Okay. So, sorry. So we're looking at problem 3, I believe. So we have blood alcohol concentration of 8 adult subjects of rapid consumption of 30 milliliters of ethanol. The table shows the data they obtained by averaging the blood alcohol content in milligrams per milliliters of the 8 subjects. So in this table, we have the concentration of blood alcohol after a certain amount of time. And so we can see, after these are weird measurements of time, but after 0.2 hours, the content was, 0.25 milligrams per milliliters. After another, I feel like that's supposed to be 0.25 instead of 0.20, but oh well, I'm not going to judge, right? I feel like I should point out that does seem like a mistake, because every other time interval is 15 minutes, which is a quarter of an hour, and this first time interval is not that. So I feel like that's just an error, and it's meant to be 0.25 there. So the question first asks, what is the meaning of C prime of t, and what are its units? So when you're talking about the derivative of something, so I'm talking about C prime of t, which is the derivative, which I'm going to write like this, the derivative, oh, sorry, I should stop. I'm going to stop sharing my screen so you guys can see what I'm writing. So the derivative of something, which I can write like this. So notice that the variable here is time. So if I'm asking you what the derivative is of some function of time, what we're really asking here is, how is this thing changing as time is changing? In fact, that's what a derivative means in general. So when someone writes, like dy dx, what they're really saying is this is how the top thing is changing, how y is changing as x is changing. Now that's a lot of words for what they really mean. People usually kind of slim that down to the rate of change of y with respect to x. But when I say those words, I really mean these words. I mean how y is changing as x is changing. This here, right, which you could totally write as dc dt, is the rate of change of c with respect to t, or how c is changing as time is changing. A rate of change. That's all derivatives are. So this is really saying the derivative here is how the blood alcohol content is changing, or I should say blood alcohol concentration is changing as time is changing. So if I had to answer this question, I'd probably say it's the rate of change of C of t, which is the BAC. And that's always what, so like if someone ever says, what's this derivative mean? You'd be like, oh, it's the rate of change of the thing it's the derivative of. Now, in this particular case, they also ask what the units are. And almost always the units of something are the units you started with divided by the units of the thing of the variable you're differentiating with respect to. So blood alcohol concentration is measured in, what do they say, milligrams per milliliter, right? So C, that's in milligrams per milliliter. You can really actually kind of think of it as division. What is time measured in this particular problem? I don't even know. I guess it's hours. So you could say, oh, dc dt, the rate of change of blood alcohol concentration is milligrams per milliliter per hour. And that's kind of how you would answer that first part. I'm definitely not going to construct a table of estimated values for the derivative. I'm happy to help anyone with that during office hours, but I will say is the way you would talk about constructing or constructing a rate of change rate is, and again, that's of estimated values. So again, right, we've kind of laid it out here. The derivative is the change in blood alcohol concentration with respect to time. So it's the change in blood alcohol concentration divided by the change in time. So you could say, like, I'll talk about the first one. If you start at, I'm gonna make the assumption that it's really supposed to be 0.25 hours. So if you go from 0.0 hours to 0.25 hours, and your blood alcohol concentration goes from 0 to 0.25, then your rate of change is 0.25 minus 0 over 0.25 minus 0, which seems kind of dumb. Maybe that's why they made it 0.2, I don't know. Which is 1 milligram per milliliter per hour. That's what happened in the first 15 minutes. You went up by 1 milligram per milliliter per hour. And so it's just kind of the difference between the average rate of change and the instantaneous rate of change, right? They're asking you to compute average rates of change in this problem. Okay. Never enough time. So let me go back. So I'm happy to talk more about that problem with anyone who wants to talk about it in office hours. But what I will say, so I think, and I'm not quite sure, I think at the end of last class, we kind of started talking about the derivative of sine and cosine. Yeah, go ahead, Emily.
I have a quick question about the this equation of the tangent line. If you are given the things to have the equation of the tangent line, can you use that to estimate the derivative of something else?
Yes, definitely.
Okay, I was just trying to make sure because I had a question on that for one of my homework.
Sure. Yeah. So the tangent line, again, the slope of the tangent line is the derivative at that particular tangent point.
Mm-hmm. Okay, yeah. Thank you.
You're welcome. So I don't remember because I teach a lot of this material to different people. I think last class we talked about how the derivative of sine of x is equal to cosine of x. And we did that graphically. Does that sound familiar? You guys are like, maybe?
Yeah.
Okay, good. It's also, and I think we also said that the derivative of cosine of x is equal to negative sine of x in the same sort of way. And while we certainly could do these with the limit definition, and I'm happy to not today, not because we can't, just because I'd rather use our last 10 minutes a little more efficiently. So if you guys want to see the limit definition of these derivatives, we can do that at the beginning of class on Tuesday if you ask me to, if you want that. Or you can send me an email over the weekend or somehow communicate that you would like to see that. But what I want to do now is actually talk about the product rule for a second. So product rule, well, let me just point out, here is not the product rule. So if I was going to try and take the derivative of two things multiplied together, say like the derivative of, I don't know, x squared times x cubed. Here's what it's not equal to. It's not equal to the derivative of x squared times the derivative of x cubed. I want to make it very, very, very clear. When you take the derivative of a product, you can't just differentiate each factor separately and multiply the results together. Why not? Well, because it doesn't work. X squared times x cubed is x to the fifth. And you guys do know the derivative of x to the fifth is what?
5x to the fourth.
Exactly. And if you look over here, that's definitely not 5x to the fourth. 2 times 3 is 6. X times x squared is x cubed. So I really, really, really like so many reallys, all the reallys, want to emphasize You can't take the derivative of a product by differentiating the factors and multiplying the results together. The reason I mentioned this so strongly with this example is because it's much easier to want to do it when you can't just multiply it out. So I want to also say that the derivative of x cubed times sine of x is definitely not equal to 3x squared times cosine of x. Does not work that way. For the same reason this doesn't work. So what is the derivative? Well, that's a good question. There's this rule called the product rule. We can also start class on Tuesday by showing you how to derive the product rule if you would like to see that. But here is the way it works. The product rule says if you're taking the derivative of a product of functions, f times g, or f of x times g of x if you want to be more kind of long about it, although I'm going to write the short way in a minute, equal to f prime of x times regular g of x plus regular f of x times the derivative of g of x, or g prime of x. And the way I always kind of think about this is the derivative of one thing times the not derivative of the other thing plus, and then you switch it, or vice versa. So you get the derivative of each part times the not derivative of the other part in every way possible. So f prime times g plus f times g prime. And usually people often write this much more compactly as f times g prime equals f prime g plus f g prime. We don't write the x's because we know they're both functions of x, or whatever variable you happen to be using, right? They might be both functions of y or z or whatever. The variable doesn't matter. It's the functions that matter. So back to the example we actually know. Let's take a look at the derivative of, what did I say before? X squared times x cubed. So now I'm going to use the product rule. It's okay. This is my f. And this is my g. And the derivative of f times g should be f prime. So that's, in fact, let's write ourselves up the little spots here. It's going to be f prime times g plus f times g prime. And in this case, f prime is going to be 2x. G is still x cubed. Plus, there always has to be a plus when you're doing a product rule, right? It's something plus some other thing. F, which is x squared, times g prime, the derivative of x cubed is 3x squared. And now we're going to simplify. 2x times x cubed is 2x to the fourth. X squared times 3x squared is 3x to the fourth. And when you add those together, you get 5x to the fourth, which is the right answer because we know that the derivative of x squared times x cubed is really just the derivative of x to the fifth, which is 5x to the fourth. So we can at least see in this example that, oh yeah, it seems pretty clear that the product rule actually does work as we think it's supposed to. But then we can use that to find the derivatives of things, of products of things that you can't just multiply out, right? There's no multiplying out x cubed times sine of x. It is what it is. And the only way to differentiate it is by using the product rule. So here we say, oh, well, the derivative of that's going to be the derivative of the first thing, which is 3x squared times the not derivative of the second thing, plus, and then we switch it up. I did the derivative of this one last time, so I'm going to leave that one alone this time. And I left that one alone this last time, so I'm going to do the derivative of that one this time, which is cosine of x. And that would be my final answer here. So we can use the product rule. I mean, eventually, once we have a few more functions under our belt, we use the product rule for all kinds of things. Gosh, I'm really having trouble remembering all the things we've done. Have we also done the derivative of e to the x? Did we learn yet that the derivative of e to the x is equal to e to the x? Maybe. It's okay. The answer is no.
I don't think we have.
Okay. All right. Cool. We'll talk about that in the near future. Sorry, it's hard to 21A and 17A, there's a lot of overlap and there's a lot of not overlap. And like, have I done that in this class or the other one? But we can also look at something like, the derivative of x to the fourth times cosine of x. And the same kind of idea applies. It's going to be 4x cubed times cosine of x plus x to the fourth times the derivative of cosine, which is negative sine of x. And here I would definitely rewrite this. So usually we don't simplify these a lot unless we're asked to. But I definitely would take the one step of writing this as 4x cubed times cosine of x minus x to the fourth times sine of x. It is pretty standard notation to write constants and powers of x before trig functions. So let me go one more because there's one last thing I want to say. I mean, really, there's a lot more things I want to say about the product rule. But there's one last thing I'll say in the less than a minute we have left. So the product rule can actually be extended to more than just a product of two things. For example, I could totally say I want to take the derivative of x to the sixth times sine of x times cosine of x. And the way I'm going to think about this is by thinking of it as a product of two things. Here's my first thing. Here's my second thing. So I'm going to call this, H. I'm going to call this K. So I know that using the product rule, the derivative should be H prime K plus H K prime, right? Derivative of this times that plus this times the derivative of that. But H prime, I'm going to have to leave as is for a moment. So I'm going to say H prime is just x to the sixth times sine of x prime. K is just cosine of x. And then H is just x to the sixth sine of x. And K prime is the derivative of cosine, which is negative sine. But now I have to take the derivative of x to the sixth sine of x. I'm going to have to use the product rule again. So the derivative of x to the sixth sine of x is going to be the derivative of the first part, which is 6x to the fifth, times leave sine of x alone, plus now we leave x to the sixth alone. Oh, yeah, I'm good. Times derivative of sine of x, which is cosine of x. And all of that derivative is still multiplied by cosine. And then I have this, which is plus x to the sixth sine of x times minus sine of x. And hold on, I do have something kind of worthwhile. I know I'm over time. Let me just multiply this out and then I'll say it. So 6x to the fifth sine of x times cosine of x plus x to the sixth times cosine of x times cosine of x. Yes, you can write that as cosine squared. I'm not going to write this down. Plus x to the sixth times sine of x times the negative sine of x. Here's the thing I want you to see. When you have the derivative of a triple product, something times something times something, you get 1, 2, 3 pieces. So derivative of 3 factors, you get 3 pieces, and each piece has exactly 1 derivative and the other 2 not derivatives. So this first piece has the derivative of x to the sixth, which is 6x to the fifth, times sine times cosine. The second piece has the derivative of sine, right, I'll circle the derivatives, times the not derivative of x to the sixth and the not derivative of cosine. And this last piece has the derivative of cosine times the other 2 not derivatives. And this idea, this pattern holds for a derivative of a product of any number of factors. So you could have 4 factors or 5 factors or 17 factors. And if you take the derivative, you would get that many pieces, and each piece would have 1 derivative and the rest of the functions not derivatives. And you'd have to cycle through having each of the different functions derivatives show up.